Hello, everybody. Today, we're going to continue with where we left off yesterday, going over basically the Riemann sum formula and how we can use it to find the definite integral. So here, let me share my screen real quick. So just as a brief summary, like I said, we talked yesterday about why this formula, basically when we're trying to find the area under the curve, how we can do that. And basically the idea is that we break it into rectangles, find the area of each of those rectangles, and then I won't go through everything we did yesterday, but basically what we get is this formula in the end. And now we're going to talk about how we can actually use this formula and what we can do with it specifically. So here, um, let me say this basically, and again, I won't go over everything we did today. If you want to kind of see or everything we did yesterday, if you want to check that out, by all means, just take a look at what we did yesterday. But what I will say is that this formula, first off, as we mentioned, is just an approximation. Now, how do we actually find these? There's a couple ways. So what I really want to focus on is this first, because this, this we've kind of explained the others here. And actually, let me redraw kind of a basic setup here. So here, remember we have, I can redraw this. We have like some a value, and then we have some b value, and then we have some function, some kind of function f of x, right? And then, oops, and then basically what we're trying to do, remember, is approximate the area under the curve. The way we do that is by drawing partitions. So that'll be like the first partition, that'll be like the second partition, third partition, so on and so forth. So there's a couple things that we want to do, because obviously we ended up with this formula, but like how do we actually use it? That's what we want to cover today. So here's how. We need to figure out, remember this, we talked about the summation. So like however, this is just however many rectangles we have, we add them up. This is the real formula. And what you actually want to start with is delta x. So how do we find delta x? That's the first question. Remember, delta x is like the width of each partition, so that would be delta x. And again, delta x could be different for each partition, like we talked about yesterday, but we don't want it to be, right? We want it to be the same length, just to make our lives easier. This happens a lot with integrals, by the way. There's a lot of things with integrals where we could we could make them different and a little bit more abstract, but our life actually gets a lot easier if we make them more, or if we make things consistent, basically. So even though delta x could be the same, we don't want it to. We don't want to deal with it changing for each partition. It's easier if we just keep it the same. Now, if we do keep it the same, what would it be, or how would we find it? Think about it. Go ahead and pause the video maybe if you want to think about it. But the way that we would find that is, first off, find the total width of the shape, right? If we're trying to find the area of this shape, so if we're trying to find the area of this shape, what would that equal? Hopefully it's clear. B minus A. And again, think about it. If this is like, I'm just making this up, but if this is 5 and this is 1, well, what's the distance between those? 4. 5 minus 1. So B minus A in general. So delta x, I'll say, is equal to B minus A. Well, not exactly. That's the entire distance. And then delta x, let's say we have, the way I'm drawing this, let's say we have n rectangles. Again, n could be anything. But let's say we have n rectangles. Well, if you take the entire distance and you just divide it by the number of rectangles, hopefully it's clear that you'll actually get the width of each individual rectangle. So this is the general formula for how you find delta x, and you need that on every problem. The next thing we need to understand is how we essentially choose this, how we choose our sample point. Now, to be clear, we talked about this yesterday, but when you're talking about, x, what we're really trying to find is x star k. There's a couple ways, or a couple things to keep in mind. So the first thing, actually, yeah, let me just move this up slightly. So the first thing to keep in mind is that, like, let's say if we're talking about, and actually let's do this. Let's talk about x star. Let's talk about x star 1 for a second. So like what this means, remember, is a sample x value in the first partition. So in the first partition, let me draw that. So Actually, let me get rid of this box just to get a little bit more room so I don't have to keep scrolling. So there you go. So basically, if we're trying to find delta x1, think about it. We mentioned yesterday that you can basically pick any x value you want as long as it's in the first partition. And then once you find it, once you find that x value, you basically plug it into the function, you get a certain output, and that output is the height of the rectangle at that point. So you can choose any x value in between here, and if we do that, hopefully it's clear. We'll get some y value between. We'll get some y value basically here, some height here. What you cannot do is you cannot plug in a value outside of the first partition. That will give you like a height here or like here. This is not a height. You need to choose a height. You need to choose an x value in the first partition so that you get a height within the first partition, basically. And that's going to be pretty close. That's the idea, right? If we allow ourselves to pick any x value, that's not going to be good at all, right? If I pick this height, well, that's not even close to the height. But if we have to pick between here and here, like no matter what we do, it's pretty good. That's the idea. So now, again, it's kind of like what we said before with the delta x. You could make the delta x different, but it's actually your life gets easier if you make it the same or pick it the same way or make the delta x the same in each partition. Similarly, you could pick a different delta x, or you could pick a different sample point. So you could pick like a sample point here in the first partition. You could pick a sample point here in the second, here in the third, somewhere in between in the fourth. You could like pick at a different spot basically in each partition if you wanted to, but you shouldn't. Like the definition allows you to. Again, the star basically means we can pick any sample point we want, but even though we can, we should not. Our life actually gets a lot easier if we're consistent about how we pick them. And when it comes to like that kind of consistency, there's really like a couple strategies, and we'll talk through some of them now. So the first strategy I'll say is called the left Riemann sum. So here, let me break this apart. Or let me see if I can raise this up a little bit as well. There we go. So the first strategy is called the left Riemann sum. So the left Riemann sum, what does that mean? So I'll say we'll start with the left. So with the left Riemann sum, this is basically what it means. So first, think about it. What would x star 1 be? So x star 1, go ahead and pause the video and think about it. But basically the left Riemann sum means like for every partition, you just choose the x value furthest to the left that is still in the partition. So what would that be in this case? Hopefully it's clear that it's just the a value. Whatever the a value is, that's the left point, right? And then you can do x star 2. What does that equal? In the second partition, what's the leftmost value? Hopefully it's clear. It's actually, and pause the video if you're not sure, and then assuming you've unpaused it, a plus delta x. So think about it. You have a is this distance, delta x is this distance. We want that entire distance, whatever that x coordinate is, that entire distance, that's a plus delta x. So a plus delta x. And then we could keep going. So, and actually, let's hold on. Let's come back to this actually. So that's the logic for the left. Let's actually start at the right. I think it's actually easier to start at the right. So that's the kind of logic we're getting. We're going to use similar logic. But if we're starting with the right, so you're in the first partition, if I go to the right, hopefully you can see that the right is actually the same, like x star 1 would actually be the same as it was in the left, like for the x2 of the left, which kind of makes sense, right? The rightmost point of the first partition is the leftmost point of the second partition. That's the dividing line. It's saying the same thing. And here, if we have x star 2, what would x star 2 equal? Basically, it would be like in second partition, all the way to the right, that would be a plus delta x plus delta x, or in other words, a plus 2 times delta x. And then in the third, you can probably see where this is going. It would be the third, basically. So like x star, I'll just finish that real quick. X star 3 would equal a plus 3 times delta x, right? Because you go start from 0, go to a, that's a plus 1 delta x plus 2 delta x plus 3 delta x. That would put you right here for the right of the third partition. But this is the third partition. So hopefully that logic makes sense. And then now what we really want to do is we want to come up with a general formula that will always work. So what's a formula that would work for like x star k? And the way you do this is kind of tricky, but the way you do it is you essentially look at all the individual cases you found above. You first identify what stays the same. So like if you notice, the a plus and the delta x, those stay the same between each of these, right? So what that means is that we're going to have a plus in the delta x. That's always going to stay the same. And then think about what's changing. What's changing is this number in front. So once you recognize what's changing, what you need to do is you need to find some formula that relates the subscript. You think of the subscript, like the k, as the input to the function. And then think about it like what formula, if I plug in k for each case, gives the correct thing here. And hopefully you can tell that actually the answer here is just k times delta x. Why is it k times delta x? Basically, because like whatever the subscript is here, like 2, that's what the k value is there. So when you think about it, this is going to be a plus k times delta x. So this is a special formula to do the right, basically do the right bound, like the right Riemann sum in every partition. That's good. Now, if we look at the left, again, we've already talked about like kind of the first two cases. If we're now talking about like x star 3, so let's do x star 3. What is that? So in the third partition, all the way to the left, hopefully it's clear that that's actually a plus 2 delta x. So a plus 2 delta x. And now we want to do kind of the same thing that we did before. So we want to basically find x star k. How would we find x star k? Again, it's kind of the same thing. The a is going to stay the same. Now here, this looks a little weird, right? We don't actually see a delta x here, and that might make it tricky. But what if you think about it like this? What if you imagine plus 0 times delta x? Maybe that'll make it make more sense. So when you think of it like that, it's not that the delta x is not there. It is there. It's just that we're multiplying by 0 first. Looking at it that way makes it a lot easier to figure out what the coefficient is. And then basically what we want, again, the only part that changes is the k value in front of the delta x. So think about it. We want some, like when you plug in 3, we want to get 2. When you plug in 2, we want to get 1. When you plug in 1, we want to get 0. What formula would do that for k? Hopefully it's clear. K minus 1. So that is the special formula that allows, like if you just follow this formula, like in here, like in the integral, or in the like the Riemann sum, that will allow you to pick the right value. And then one other thing I'll say for the right Riemann sum. So for the right Riemann, or sorry, we already did the right. I mean the midpoint. That's the other way you can choose. So you can choose the left, like for each partition. Like for the first partition, you go all the way to the left, all the way to the right, or dead smack in the middle. So how would we do that? So for x star 1, what would that be? Hopefully it's clear that it would be a plus 1/2 delta x. So a plus, I'll say 0.5 times delta x. And then what would, the midpoint of the second partition would be right there. What's that? Hopefully it's clear. It's a plus 1.5 delta x. So a, basically x star 2 is a plus 1.5 times delta x. And what's in the middle of the third? What's that? So x star 3, you probably see where this is going. A plus 2.5 times delta x. Right? And then what we want to do, again, is kind of similar, the same thing basically that we were doing last time. Yeah, the same thing that we were doing last time. We want to find a formula for the general x star k. So x star k is equal to what? What stays the same? So this stays the same. So that'll be a plus, so a plus, that stays the same. This is the only thing that's changing. So we need some formula that relates like whatever the k value is to that. So 3's got to go to 2.5. 2's got to go to 1.5. 1's got to go to 0.5. Hopefully, if you notice, the formula is k minus 0.5. Right? So if you multiply each of those, so like k, or what's x star, k would be a, I'm just going to write with more room, k minus 0.5 times delta x. So hopefully looking at it that way makes sense. And basically the idea, you can check this, right? If you plug in k equals 3, This will be a plus 2.5 delta x, just like we said it should be. That works out. And it works out with all the other ones too. So that's the basic idea. Now, to be clear, these are not the only rules you could have. These are generally, like for Riemann sums, the only rules that you're supposed to remember. But you could remember a lot of other rules too. So, for example, you could invent, if you wanted, a 25% rule. And that the rule is basically for every partition, you go 25% from the left and you choose that sample point. How would that work? What would the actual formula be? Pause the video and see if you can figure it out. Basically, it would not be k minus 0.25, it would be k minus 0.75. So here's another way of thinking about this. Of these three formulas, by the way, you can kind of ask the question, which one is the simplest? There's clearly one here that is simpler than the others. And if you notice, it's this one, right? So like the right Riemann sum doesn't have a minus something here. It's just, you can look at it as k minus 0 if you want, but it doesn't have a minus anything there. So the way I actually like to think of these, I like to think of like the left in the midpoint as basically the right Riemann sum, but you just back up. So here, let me show what I mean. So here, and again, we don't really care. We don't even care about the function. We've kind of abstracted that away. What we really just care about is like this visual, like on the x-axis. So if you think about it like this, like another way you could write this formula is x star k equals a plus k times delta, or oops, k times delta x. If I can draw today, let's see. K times delta x minus delta x. So if I just distribute the delta x in, this is the right Riemann sum, right? A plus k delta x, we just said that was the right Riemann sum. And then you just back up a delta x, right? And then if you want to do this a similar thing, and doesn't that kind of make sense, right? Like if you, like, what does that mean? It means if you want to go like to any partition, let's say the second partition, and you want to find the left Riemann sum, just find the right Riemann sum right there, and then back up a full delta x. That'll automatically put you at the left. That's one way of looking at it. And then here we have with the midpoint, we have a similar situation. So if I distribute, I get a plus k delta x minus 0.5 delta x. So what this one's saying, again, it's kind of like this spot right here is the right, a plus k delta x. So like in the second partition, if you want to find the midpoint, you find the right Riemann sum, and then you just back up a half of the delta x, which makes sense. So you can make up your own rules to do anything. Like you can make up a rule that says, oh, how could I have a formula that makes me pick 33% from the left, like a third from the left in every partition? Well, it would just be a plus and then k minus 0.67. The way we're looking at it, right? You do like this is the right Riemann sum, and then you would have to back up not 0.33, because remember, you'd be backing up from the right. So you'd be backing up 0.67. So you could come up, if you wanted to, with like a 25% rule, a 50, well, we have a 50% rule, the midpoint rule, 75% rule, 1/3 rule, 2/3 rule. You can make up whatever numbers you want. There's an infinite amount of spots you could pick to be consistent, but these are the main ones that are the easiest. So these are not the only ones you could make up, but you could generalize this formula to work for anything, but these are the main ones that matter. And now once you get this, again, we're gonna talk about how to actually use this later, like how to calculate it. But for right now, obviously, we're just kind of talking about how to actually use the formula in practice. And then tomorrow, what we're going to do is go over how to do a worked example using actual numbers, so that this makes more sense. So there you go. Hopefully that all makes sense. Yeah. So if you have any questions, feel free to just drop them below in the comments. Otherwise, I will catch you next time. See you.